Okay, so welcome everyone to the last session with 3 talks. The first talk is given by Pedro Valero-Lara on multi-GPU performance, portable solution for array programming based on Kokkos. Welcome.
Thank you for the introduction. So, hi everybody. It's great to be here. So, my name is Pedro Valero. I'm a computer scientist at the ARRAY'23 National Laboratory. I'm going to present some ideas that we have been working on in the last couple of years, more or less, on Kokkos programming model. So the motivation of this work is basically, to have to help to have a programming or highly programming productivity solution. This is just, an idea about the. There are different diagrams from different, DOE big supercomputer today. So although some of them, in terms of at architecture level, they can look similar. So basically, we have 1 or 2 CPUs, and then we have a relatively large number of GPUs, and these GPUs are connected between them with a very high bandwidth network, and also the GPUs are connected with the CPUs. The programming models, the programming tools that we have to, program or to implement code on all of these, in some cases are completely different. They come from vendor, so we have to adapt one code to the other, or we have to change our code of our application if we want to make use of this new hardware or new architecture or different architecture. So the idea is to have this kind of solution that I call agnostic programming models, programming solution. Here I have found some interesting definitions about that. But at the end of the day, I think that the idea is to have a proactive, environment than reactive, What it means, so basically having one single code that can be run more or less well, or can obtain a good performance, on many different kind of architecture or different kind of platforms. So Kokkos is one of these solutions. There are others like Raya, there are others on top of Fortran as well. Kokkos is on top of C++. Basically, Kokkos is a front-end C++ library implemented on different backends. So every backend is basically a programming model that you need for one specific architecture, right? But the beauty or what is interesting in Kokkos is that one single code can be running on many different platform architecture without changing one line of code. It's only necessary to compilation time to decide which backend to use, and then you have that code. You can generate a binary of that code for one specific architecture. But then, if you want to use a different architecture, the only thing that you have to do is to compile again the code, but using a different backend at compilation time. And that is, you can select that at compilation time. So Kokkos programming model is bigger and bigger, but maybe the most important characteristics of feature are the Kokkos malloc and Kokkos views, basically how you allocate memory, the different data parallel execution constructs that we have is parallel for, parallel reduce, parallel scan, different APIs depending on the shape or layout of the data that you want to use. For instance, single range, if you are going to use only vectors. Multi-dimensional range, you are going to work on matrices or n-dimensional arrays. Hierarchical parallelism. It's a kind of, it's difficult to me to explain what is hierarchical parallelism. It's like a mix between multi-dimensional and nested parallelism. It's a way to have more control and potentially to have better performance. Okay, but it's not guaranteed. And then what else? And this is a piece of code, a very simple piece of code. That compute ASCII operation, a very simple BLAST level 1 operation, writing in Kokkos, right? So in this talk, I'm going to focus on parallel for and single range, And here you can see, a diagram about Kokkos, the different backends. As I said before, right? So at compilation time, the programmer must decide which backend to use, which is basically each backend is associated to one architecture. Recently, we have also implemented the OpenACC backend. And what OpenACC backend makes different to the other is that maybe, a runtime in a transparent way, you can deploy Kokkos code either on CPU and GPU. But this is a different work that we did. I just wanted to take advantage of, being here and just promote one of these work that we did recently on Kokkak. Kokkak is the OpenACC backend of Kokkos, and I say before, we have extra level of, we have more capacities that although these capacities, are different to what Kokkos or why Kokkos was, implemented originally, are capacities that we can exploit thanks to having this OpenACC, backend. So, but this is different work. So I just wanted to let you know that we are working on many different directions, on Kokkos to make Kokkos, more, simpler to use and exploit new capabilities. The capability that or the feature that I focus in this talk is the use of multi-GPUs or the support of multi-GPUs in Kokkos. So basically, as we can see in this diagram, we have implemented this feature right now on top of CUDA and backend, and the idea is to use multiple GPUs in a very transparent manner. Okay. We can also implement this feature in other different backend like SQL, OpenMP Target, or OpenACC, but we have not implemented those yet. So we make use of OpenMP plus any backend that is selected at compilation time to implement this new capacity. We use ARRAY's a different indexing. I will present you how to do that. And also we have some autotuning effort as well, because not always using more GPUs is going to give you more performance. So depend on the computational cost that or the kind of computation that you want to do on your multi-GPU node. So this is how it looks like. So on the left we have a very simple piece of code using Kokkos API, and this is the API that we propose and we implemented. So it's quite similar. The only difference is that, well, we have changed the name a little bit to the function that we need to make the allocations. Also, the way that the lambdas are implemented are different. So unlike the original, Kokkos, where we have only one index, here we have two indexes. So one is basically the first index corresponds to the memory space. So as I said before, this is for multi-GPU, right? So I in this, or the I index in this case, indicate the GPU, or the GPU ID, and then N correspond to the specific location of that space of memory, or that array that we have allocated in that specific space of memory, and N correspond to one element of that, right? And then the same, so we can make basically the same operation that we are doing here, but instead of using just one GPU, here we are using multiple GPUs. Yeah, I think this is all. Yeah, in this slide. The sample that I presented before in the previous slide is a very simple one. So we assume that every iteration is independent each other. So it means that they are not data dependencies or race condition. But there are, in many cases, there are many SPC applications that need what we call, stencil, right? So basically, it means that if I want to compute one element, I need to access to contiguous elements of that element, right? So this is very common in many different algorithms in SPC, Jacobi, image processing, CFD. You can find this kind of pattern in many different applications. So multi-GPU is not such a different, to a very, classic distributed memory, environments. So to deal with these things, with this stencil aware or stencil computation, we have to transfer, some data from one memory space to the other, right? So how we implemented this, we wanted to deal with that, or we implemented a syntacsis, a Kokkos-based syntacsis, to have this capacity, but again, the programmer or the user don't have the control on that. So all this communication that we have to do are completely transparent to the user. So we provide, but we have to change the API a little bit. So what we need for the user is basically one new parameter, or one more parameter that indicate us the size of that stencil. And that's it. Also, one more thing is that in the lambdas, we have included one more index, just to indicate, the global boundaries of the arrays. So when we have we have one single array distributed in many different, in this case, GPUs. So it's very typical in many applications that you have to make some particular, computations in the boundaries of these arrays. So for instance, in some boundary condition, for instance, for CFD applications. So to deal with that and to have that capacity for the user, we have added this additional, index. All these indices are controlled by the library underneath. So the user don't have to worry about what are the values of these indices. This is controlled by the library, okay? The user only has to define what are the operations that they want to do on the different arrays, basically. So autotuning. Okay, so we extended these different syntaxes or these different APIs that I presented previously, and to add capacity for autotuning. So basically, we have added two more functions to the Kokkos specification, just to have to compute the proper number of GPUs to use, basically. So we have one for no stencil aware, application where every iteration of the operation on different arrays are completely independent of each other. And then we have the stencil one when we have to make some kind of, communication between the different, arrays or the different pieces of the arrays located in different, GPUs. So, but still, the user, if they want to keep control on that, on the number of GPUs, they can just pass as argument the number of GPUs on the different, new, Kokkos API, and that's totally fine. So the user can rely on the library or can rely on themselves to specify or indicate the number of GPU that they want to use. So today it's possible to use multi-GPUs in Kokkos, but you need to have something on top of Kokkos to deal with the memory communication between the GPUs, or to just deploy Kokkos on different GPUs in this case. So here we can see an example of that MPI class code, and this is an example of the specification that we provide or we implemented to deal with to have this multi-GPU support in Kokkos without having, MPI or having something on top of Kokkos. So we can see that in terms of number of lines, the new specification is requires much less number of lines than the MPI one. And only that, I mean, it also is much simpler, right, to implement that MPI code. But the advantage of having something like the specification that we propose for Kokkos is that it's not only simple, but also allows us to have things like autotuning to make a better, exploitation of different GPUs. And all of that is completely transparent to the user. So yeah, I think that's all in this slide. So performance evaluation. So we have evaluated this new API on two different machines, Summit and Frontier. Summit is the current top number 5 fastest supercomputer in the world, in the top 500 list, and Frontier is today the top one. On Summit we have six NVIDIA GPUs, V100, and on Frontier we have 4 but in fact we have 8 because we have 2 GPU chips in one die, right? So in total we have 8. So some characteristics about the bandwidth and performance and the GPU network, etc. So this is our testbed, and then we have used 2 relatively simple benchmarks. One of them is just a basic, a very basic operation like ASPI, BLAS level 1 ASPI. And in the stencil, we basically emulate the basically a Jacobi, operation. So here the black line corresponds to the time consumed by original Kokkos using one single GPU. The red line here corresponds to the MPI plus Kokkos variant, and the blue line here corresponds to the multi-GPU Kokkos support that we have implemented. The red line here that you can see here corresponds to the multi-GPU Kokkos API without autotuning, and the blue one is with autotuning. So for no-stencil aware, computation like ASPI, where every iteration is completely independent between them, and we don't have to deal with race condition or data communication. So we see that, okay, our implementation, the one using autotuning or not, is very similar. It scales well. It's faster than MPI, and well, it scales relatively well. Here at the bottom, we can find the same analysis, but we present the scalability and also the number of GPUs that we are using for the autotuning. So basically, the autotuning version, or the version that makes use of the autotuning capacity that we implement, is able to, select, the different and change the number of GPUs to use. So this is very important, in particular for things like for stencil-aware operations, where, as you can see here, by changing the number of GPUs, we are able, to make a better, exploitation of the resources that we have. If we don't, for instance, in the red line that we can see here, we see the same multi-GPU support, but without using autotuning. So basically, we are using all the GPUs that we have in this case Summit. And the problem with that is that when the computation that we have to do is not large enough, the time consumed by the communication is dominating the overall execution time. So this is something that we can, fix, or we can have better performance by using the autotuning version, right, or the autotune version. So the same story for Crusher. In Crusher, well, here we see, as we have a much larger number of GPUs, so we see the transition from using all the GPUs to using a lower number of GPUs happen before, but the conclusions are basically the same. And well, once again, I think this is important. Unless what I say that is important is maybe not this word or maybe not Kokkos, but this context, this idea of having more and more agnostic programming models. And well, the conclusions. So I think that with this new multi-GPU API for Kokkos, we are able to increase the programming productivity for Kokkos application, in particular for those applications that need or want to use more than one GPU. We have autotuning that I think that makes sense, is important, and it's completely transparent, to the users. And again, I mean, this is an interoperable solution, so you can still use MPI, for instance, for not for GPU communication, but maybe for node-to-node communication, And future work, well, here in this work we have focused on parallel for and single range, so we can implement other features as well, like parallel views or Kokkos views for multi-dimensional arrays, and also implement this capacity in the other backends. And as I said before, extend the support for distributed node systems. Some references, so if you are interested in this work or you want to use this, new API, you can access to this repository, and you have all the codes, all the tests that we did, and also for instance, the MPI plus Kokkos code. You also have that in this repository. A reference about other effort that we are doing on more or less the same direction. One other interesting reference, Jan Sesko is a Sandia researcher. He's also part of the Kokkos team, and he is implementing like a different idea for multi-GPU support with Kokkos, and you can find other, a good reference there. Also, I think that this is also part. There is one repository somewhere where you can also use his approach for this, and I think that this is all. Yeah, this is all. Thank you.
Questions?
Oh, many questions.
Thanks. I noticed that you had a benchmark using some AMD GPU cores. Is there a use case that many people are using those for right now?
What do you mean about benchmark on AMD GPUs?
You mentioned that one of the nodes that you benchmarked, I saw this in your paper, was in a multi-core AMD graphics die.
Yeah, you mean Frontier?
I think so.
Yeah. Frontier is well, in this case, I'm using only GPUs, so I'm using AMD GPUs. Yes.
Yeah. Is there what kind of use case are people using AMD GPUs for? Most of the compute workloads are using some form of CUDA right now.
I mean, anything or any benchmark that can be used for or is used for CUDA can be used also for AMD GPUs. There is nothing in particular in terms of benchmarking or that is very particular to AMD GPUs only. I mean, you can take a look at the ORNL website or OLCF website, and you will find many different benchmarks that have been already, analyzed on Frontier and different kind of workloads. I don't know if I'm answering your question. Sorry. Yeah.
Okay. Yeah. Is it ML applications that people are using that system for?
I mean, there are many ML machine learning. You mean?
Yeah.
There are many different machine learning. Also, they are trying to deploy or use ML libraries. I think that in AMD they are trying to support some capacity or some also implementing some other, support for that. I mean, yeah, there are many things.
Okay, thanks.
Yeah, sorry for not, I cannot be more concrete on that, but I'm not very involved in that. Sorry. But there are a lot of material, a lot of things that you can find in a ORNL website about that. Yeah.
So I remember reading this paper, and I really liked the idea of exposing a more transparent, accessible system that wasn't filled with a bunch of different layers. But I had two concerns or questions about the way that the API was designed, and it seemed like well, the first one was around the stenciling handling, and it wasn't clear to me how easily that API would just scale to large dimensionality in stencils. So, higher ranks, higher dimensions of that versus just a single dimension, and whether that would require like a new primitive or whether there was something obvious in terms of how to use that primitive for the user. And then like sort of layering on top of that, you had, if I recall correctly, like pairs of calls that handled different cases, and so there were like multiple different API calls for different situations, and it almost seemed like there was going to be a combinatorial explosion depending on how many different combinations of things you wanted. Is that true? And if so, what do you think about how you might improve the compositionality of the API?
No, they are very good questions. About the first one, so I focus on a single range API of Kokkos. So about having the same support, the same capacity, but for matrices, I should do the same, but for a different Kokkos API that is called an MD range. But that's possible, of course. It will require, for instance, for stencil, word computation or stencil computation, we will need, probably will require a much larger number of communications. You know, in particular, I mean, the higher the dimension of these arrays are, the more communication we will need. Also, but it's something that is possible to implement. There is nothing that we cannot implement in that direction. Yeah. So, and why about, you know, so many APIs? It's just because of, for the sake of, you know, implementation or for the sake of debugging and having, but of course, all these APIs can be merged in one single. You know, but just to, you know, have a, you know, to have a completely different implementation in terms of debugging or in terms of evaluation, you know, I decided to implement, you know, like one by one, you know, but all these API can be merged in just one. There's no problem with that. Yeah, absolutely.
Yeah. So you mentioned that you assume that the iterations are independent, right?
No. I developed different APIs.
Yeah.
In one of the APIs, I assume that the iterations
Okay. Anyway, my question is
independent, but in the other, I assume that they are not independent.
all right. Anyway, my question is really about can GPUs directly access each other's memory?
Yeah.
How is that handled at the low level? I thought that
At low level?
at the low level. I mean, what actually happens when a GPU accesses indexes an array that is kind of spread over all of the GPUs?
That is control. You know, when I, you know, let me show you. Yeah. So here I made the allocation of the different memories, right?
Yeah.
So basically this space here. So you know, when running this thing here, basically this is deployed on OpenMP plus CUDA or HIP. So I control underneath that every MPI process, or sorry, not MPI process, OpenMP threads access to the corresponding, you know, GPU memory. So just with this double indexing that I'm using, I don't have that problem. You know, I don't have to. I mean, one GPU don't really need to access to the data to other GPU. It needs to do that in case of the stencil aware. And that is why, and this again is controlled underneath.
Yeah.
And I'm using OpenMP to do that.
So what do you know what it actually does? So stencils is also quite predictable, so you could actually analyze it. But what if you do something like a permutation of an array? That's still fully independent, but there's completely unstructured dependency. So, so what do you know what actually happens at the low level? How does that possibly work?
You mean that if we do, let's say, a more chaotic memory accesses here, we are doing things like maybe every thread had to access to the rest of elements of different arrays. Yeah. Is that more or less your question? How
yes.
Can we,
how does it work?
In that case, it will require, you know, high numbers of communications.
Yeah.
And maybe in that case, when using this, you know, autotuning function that gives you the number of devices to use, maybe the answer of that very chaotic, you know, scenario will be, okay, use just one GPU. Because there are a lot of
for the tuning, sure.
For communication.
But how do you even detect that you need the communication? Is that done dynamically with virtual memory or something? I mean, how do you know when you're accessing some array element, whether it's local or remote, when you just have some...
Oh, that is controlled underneath. Basically, when you create these arrays, I compute, you know, what is which portion or which part of these arrays will be mapped on the different memories, GPU's memories. So I control that underneath. Okay.
Okay, let's thank Pedro again.
Thank you.